So this is a nice paper that addresses something very specific that I found interesting, and as always, I'm just subjectively choosing some papers to put under new findings, and you can obviously scan the horizon and find many papers that may be much more interesting for you, but this is my selection. Since it's my channel, you just have to deal with it. Okay, so risks of synchronized low yields are underestimated in climate and crop model projections. So there are two issues. One, when we talk about how climate change and global warming are increasing extremes in heavy rains and droughts, flash droughts, temperatures, they all can create local impacts on crop yields and food production. But if there are modes of climate variability that are getting triggered by global warming, like impacts on sea ice loss in the Arctic, creating jet stream meanders, which can then produce globally synchronized patterns of weather events, then they can create synchronized crop failures according to the study, and these are not estimated properly in the crop model projections because they are not captured in the climate models themselves. And the additional point is that the models used for climate projection do a reasonably good job of producing the trends, but they do not produce the variability because they are not initialized forecasts. So we'll see one of the figures for that from CMIP 3, CMIP 5, and CMIP 6 warming projection or warming simulations by the models, and that tells you that maybe they are not doing so well in capturing the weather patterns that are associated with these synchronized global patterns, which is well known, but it's a cascade into the crop models and potential impact on food security that's not well considered so far. Simultaneous harvest failures across major crop producing regions are a threat to global food security. Concurrent weather extremes driven by a strongly meandering jet stream could trigger such events, but so far this has not been quantified. Specifically, the ability of state-of-the-art crop and climate models to adequately reproduce such high-impact events is a crucial component for estimating risks to global food security. Here we find an increased likelihood of concurrent low yields during summers featuring meandering jets in observations and models. While climate models accurately simulate atmospheric patterns, associated surface weather anomalies and negative effects on crop responses are mostly underestimated in bias-adjusted simulations. So climate models have systematic or random biases, and there are statistical ways using historical data that the model biases can be corrected, and then you use that to force crop models to see what crop responses are like. Given the identified model biases, future assessments of regional and concurrent crop losses from meandering jet states remain highly uncertain. Our results suggest that model blind spots for such high impact but deeply uncertain hazards have to be anticipated and accounted for in meaningful climate risk assessments. So in general, crop failures lead to water use in a certain way, like exploiting groundwater resources and energy use to manage pumping groundwater and irrigation. So you have these nexus between food, water, and energy, which also end up being part of this story of synchronous climate patterns. I won't go into the details, but they look at these wave patterns related to the jet stream, looking at the northern hemisphere. There is the Arctic, the North Pole, and you can see the continents if you stare carefully. So these are circumglobal wave 7 and 5 patterns and associated 2-meter air temperature anomalies in ERA 5 reanalysis data and bias adjusted CMIP 6 models. So they are comparing the two to create a bias so that future projections can be understood in terms of model systematic biases. That's the best way you can do these things, considering model uncertainties and so on. So these are wave 5 is got larger scales. As you increase the wave number, the features are smaller and smaller scales. So you are looking at here A to C and G to E to G are contours at an absolute value of 3 meter per second, increasing or decreasing by 3 meters per 3 meters per second, respectively. In D to H, so A to C and E to G and D and H, we are looking at D and A. Sorry. I lost here. In D and H, contours start and an absolute value of 0.5 and increase or decrease by steps of 1. So we are looking at the various quantities here. So wave 7 A to C, wave 7 E to G, wave 5 events relative to the respective climatology in the northern hemisphere for the summer months, which means you use reanalysis climatology for computing its anomaly, and because there are biases in the models, you use model climatology to compute their anomalies and assume that even though the climatologies may be shifted, there are variabilities that are captured by both in a reasonable way. There are many ways to make sure this happens. So C to G future SSP 5 8.5 for 2045 to 2099 bias adjusted output. So you get the sense that when you make future projections, you have to use a particular scenario, and SSP 5 shared socioeconomic pathway 5 and 8.5 is the worst case scenario with no attention paid to policies, sustainability, and emissions. So you end up with a worst scenario. So that's the worst case scenario. I won't go into the details, but basically you can see that there are synchronized weather anomalies for both wave patterns, and the idea is that ERA 5 identifies them and models are doing a reasonable job of capturing them, even though they may do well in the upper level in the jet stream impact, but the surface temperature anomalies are not being done very well. Okay, these are related to various things like this. We are looking here at CMIP 3 1980 to 2000 average. So, and this is CMIP 5 relative to the 1986 to 2005, and this is the CMIP 6 relative to 1995 to 2014. There are reasons why they are looked at systematically different periods, but basically because CMIP 3 did projections from 2000 forward and CMIP 5 did projections from 2005 onward, and CMIP 6 did projections from 2015 onwards based on when the assessment reports were released. The main point here is that the observations have these ups and downs, which are due to internal variabilities like El Nino and La Nina and Atlantic multi-decadal oscillation, Pacific decadal oscillation. Volcanic eruptions are included in the forcing for the models, but nonetheless the models do for example, here is a volcanic forcing. Models do a reasonable job of capturing the trend related to forcing from greenhouse gases, solar variability, volcanoes, aerosols, land use, etc. But they do not do year-to-year variability because they are not initialized forecasts. They are just initialized in the beginning and integrated forward to simulate the climate, so they can only do the best possible warming trend given the forcing and not year-to-year variability. And is there a way to argue that they are getting better? Well, you have to judge that for yourself. But remember the main point, that if they are not doing year-to-year variability and you are worried about the future, and crop cycles are very much seasonal, they could be summer or straddling summer, fall and winter, for example, then how do we rely on the future projections of climate translating into crop yield losses, especially for these synchronous crop losses based on these global patterns of weather? So these are more details: mean response in precipitation and 2 meter temperature anomalies over major crop producing regions during wave events in reanalysis data and CMIP 6 climate models. Again, without going into details, they look at North America, Western Europe, Eastern Europe, East Africa and South Africa, I suspect. You can read the symbols, but India is here. So you can see that there are global patterns in terms of era 1960 to 2014, W5, E5, so these are different models, CMIP6, bias adjusted, historic, and CMIP6 for the future. So they are looking at the historic crop losses, mean precipitation and 2-meter temperature responses in CMIP6 bias adjusted for the historic period, and then trying to understand how the future responses projections look like. So without going into details, you can imagine that what we said before, that models underestimate their surface weather response, which is very critical for crop yield computations, crop models, and so on. So historical experiment, so this is the CMIP6 models, and this is for wave, so historical experiments and observations for wave number 5 and wave number 7 and wave number 5. And again, I won't go into details, but combined wheat and maize yield anomalies during wave event years in observations and models. Again, looking at different regions, all regions, North America, Eastern Europe, Western Europe, and India. And again, the idea is to look for synchronous negative anomalies and synchronous climate anomalies, and argue that the models are basically underestimating. So if you look at observations versus models, models are systematically underestimating synchronized crop yield losses, which can have serious impact. Just looking at the invasion of Russia on Ukraine, you can imagine how the perturbations to the food markets, fertilizers, combined with energy markets have cascaded through the system. And now you imagine that 2023 is going to have lots of crop yield losses. So you have a war going on and crop yields happening synchronized way. This is going to create serious food security issues. And as always, it's the poor and vulnerable countries, the global south, small, low income island states and so on, that end up paying a price. Okay, so that's very brief. Let's read the part of the discussion. It's a long discussion section. I'm going to just pick a few points. While climate models have been excellent in projecting the mean response to continued anthropogenic greenhouse gas emissions, as we saw, our analysis suggests that they might provide a conservative estimate of how concurrent extreme weather events driven by specific circulation regimes might evolve in future, and how they might affect regional crop yield and covariability across regions. So they might provide a conservative estimate of these things. Further, we highlight that the underestimation of surface extremes identified in CMIP5 models and impacts on yields from their bias-adjusted output still persist in most recent climate and crop simulations. So people compare a lot CMIP3, CMIP5, CMIP6, and try hard to squeeze out the differences and argue what got better. But honest answer is the differences are not that remarkable. This is what this is basically confirming. Physically constrained machine learning methods designed to maintain patterns and coherence across variables might offer an effective tool for an improved bias adjustment for more accurate impact assessments. Well, this is a good idea, but then there's no guarantee that the patterns remain stationary. So if you compute it for one period and assume it's the same for a future period, you are making some assumptions. The uncertainties added can be they may be difficult to quantify. Our study points towards potential high impact blind spots in current climate risk assessments, highlighting the urgent need for more empirical and process-based research to support model improvements in the climate and agriculture domains, supplemented by expert elicitation, qualitative storylines, and decision-centric approaches. Evidence for high-risk blind spots, such as an underestimation of synchronized harvest failures, as identified here, manifests the urgency of rapid emissions reductions lest climate extremes and their complex interactions might increasingly become unmanageable. Well, this is a good call again for climate action, but calls for mitigation rather than adaptation, because the crop selections and where some crops may become not possible, or you may lose the ability to grow certain crops in certain regions because of climate change impacts, those also have to be considered, and not just rapid emissions reductions. That's where qualitative storylines, expert elucidations, and decision-centric approaches may come in. But there are difficulties in terms of convincing farmers to change their patterns even as climate change is changing its patterns. So that's a separate issue that has to be dealt with as well. Okay, so it's brief, but go and read the paper, look up the citations. It's a nice paper if you're interested in this kind of area of climate impact on crop yields and synchronized crop yield losses in the historic period and future projections. Okay.